All right, let's see what you guys remember about your trig life. So, first of all, when you measure a circle in degrees, how many degrees is it to make a full circle? 360 degrees. There's another unit of measure called radians. Do you remember how big a measure in radians is to complete a circle? Good, 2 pi radians. So in science classes and in math classes, when you have to do conversion between systems of measure, which we have to do in math, you write them as conversion factors, which means fractions. So instead of like this or this equal each other, you set it up like a ratio. You ignore the labels, and you take this ratio and you put it in its simplest form, because 360 over 2 pi is not the simplest form. Yeah, this is 180 over 1 pi. But that's a conversion factor, right? Which means in my math, I could use it, or I could flip it upside down and use it that way, depending on what I needed. So here's what's going to happen. I'm going to ask you guys to convert between radians and degrees. So if you have degrees, and you want to convert it to radians, do you remember which version of this conversion factor you multiply by? Good, you multiply by pi over 180. Because if you think about that, I want to cancel out the degree measurement, which would be in the denominator here, and I want to keep the radian measure, which is usually signified by a pi. Now, the reverse of that, where you have a radian measure, and you want to convert it to degree measure, you would take your conversion factor, and you'd have to flip it upside down. So you want to keep the degrees, and you want to cancel out the radians, which usually has a pi in it. So you do this a lot in dimensional analysis when you're in chemistry, but obviously those are more fun because you got a lot of things to convert. In these problems, you just got one thing to convert. So we're going to skip around as far as the examples go, but guys, don't be shy. Like if you need another example of it, let me know. I'm going to look at number 3. Right now I have a degree measurement, so I'm going to take my degree measurement, and I'm going to multiply it by pi over 180. So then sometimes kids are like, well, now what? Well, think about what you have here, guys. You have a fraction. You have a negative 135 pi being divided by 180. And I don't really know what that is off the top of my head. Well, I do, but maybe you don't because it's like the first day of the semester and we're already taking a 38-page packet. All right, so you would math enter that on your calculator and reduce the coefficient, but this reduces to negative 3/4. But don't forget, there's a pi on that factor. So this converts, negative 135 degrees is the equivalent of saying negative 3 pi over 4 radians. You don't have to label it with radians. It's kind of understood in math that if you write like a weird fraction like this with a pi, that you are referring to radians plus the context of the problem, but it doesn't hurt to label. All right, so what if we have the other direction? What if we have radians and we want to convert it to degrees? Well, we take our measurement and we multiply it by, this time I want to cancel the pi out. So I'm going to multiply it by 180 over pi. And then this fraction, it's really a cross cancellation problem, isn't it? So at the very least, I hope you see that the pi's cancel. And maybe you don't know what to do next because you're tired and you don't want to think. There is some more cross cancellation, but you can just type on your calculator negative 103 times 180. Oops, that's an 80. And then divide it by 18. Some of you saw that this 180 over 18 canceled out to a 10. So either way, you get an answer of negative 1,030 degrees. This time you do need a degree measurement on your answer. Okay, make sure you have that degree measurement symbol there. Or you wrote degrees. Questions so far? It's all coming back to you now? Like a flood. You do have to have that conversion memorized. We use it a lot in PreCalc and eventually in Calc. So coterminal. There's a really fancy definition for coterminal, but I'm going to write a less fancy version of it down here. So a coterminal would be an angle whose terminal side and I'm going to use a not very fancy term here, lands at the same position. So I'm going to kind of fly forward for a minute in our knowledge. When you are measuring angles in what looks like the coordinate plane, but eventually we're going to discover again that it's the unit circle. So like for instance, 45 degrees measured from standard position, this is standard position, 45 degrees measures up like this, right? This is 45 degrees. There's another way for you to measure an angle and still land at that same exact spot. Like what if you started in standard position but you went negatively? If you went negative 315 degrees, you would still land in the same spot. So this is an example of one relationship of angles where they are coterminal. They land in the same spot when measured from standard position. So let's talk about how we do that in degrees. So for degrees for coterminal, you take your angle, which will be measured in degrees, and then you either add or you could subtract full rotations. Well, if you're in degrees, how big is a full rotation? In degrees, 360. So I'm going to say plus 360, and then I'm going to be fancy, and I'm going to throw K on there. K represents any integer. So you could do 1 rotation, 2 rotations. You could do -1 rotation and -2 rotations. So any number of rotations. We're going to see some examples in a moment where I want it in a general form versus I want specific answers. So what about radians? How do you make rotations in radians? So you're going to take your angle, which will already be measured in radians, and this time you're going to add, what's a full rotation in radians? 2 pi. So to make it general, I'm going to call it 2 pi k. Okay, so the next 4 examples actually, I'm going to do one in a specific case and one in a general case for both radians and degrees. So I'm going to change the directions a little. You might want to like draw a line like this between 7 and 8 and between 9 and 10. So on 8 and 10, I'm going to change the directions to be like for all angles, the general case. And over here on 7 and 9, we're going to do what the directions actually ask for. So if I start with 36 degrees, and I want you to give me one positive and one negative coterminal angle. So you start with your angle, which is 36, and if I want to stay positive, I need to add a rotation to it. So a rotation in degrees would be 360. So one example of a coterminal angle who is positive to 36 is 396 degrees. Is that the only acceptable answer? I could keep adding 360. If I wanted to irritate my teacher, I would do that. You shouldn't want to irritate your teacher on a test. It's just good advice for everybody, okay? Like I have kids who add 17 rotations, like just for the fun of it. Which isn't hard, you just like 360 times 17. What's hard is your teacher then has to go figure out whether that's a good answer. And then I get mad. And then you just made me mad. And then I hulk out in the middle of your test. No, not really. Okay, what about negative? I want to go the other direction, so now I'm going to subtract a rotation. So you still start with 36, and then you're going to subtract a rotation. It has to go in that order, huh? So what is that, negative 324 degrees? So again, you could keep going, but we're not going to. We're just going to stop there. So when it says for all, meaning I want a general statement for all coterminal angles, really easy. You just take the measurement of the angle, and then you put a general statement down. So this is degree measure, right? So you're going to add 360 for whatever number of rotations you want. Now remember, k is an integer, so it could be positive or negative whole numbers. So you could be adding 7 rotations, or you could be adding -7 rotations, which is subtracting 7 rotations. So this is all you have to do for that question. You might see on my key that I wrote down -405 plus and minus 360k. That is just like an old habit of mine. I always write plus or minus down, like since I was a wee little one, your age. And I just never broke it. But your book actually might use n instead of k. So, if you see any of these answers, they all mean the same thing. Okay, so just be flexible in your interpretation of what the answer key says. So here we have radians, and this is a good case where kids get confused and then try to get the right answer regardless of the cost to their time. So they don't like radians, right? No one likes fractions. So then they convert it to degrees, they find a coterminal, and then convert it back to radians. Do you feel like that's time efficient? No. And it's really quite easy to add a rotation in radians, guys. What do? You add a rotation of 2 pi. So I know what kids don't like about this. It's the fraction. Well, y'all, when you add a fraction, you just would need common denominators. So 2 pi over 1, same thing as 6 pi over 3. And then if you were to add those together, you would get 11 pi over 3. We're going to be doing a lot of fraction work as we go through our trig. So the more comfortable you get with your 4th and 5th grade fractions, the better off you'll be. And you won't have to stress about it so much. So again, that's not the only answer, but that's the first one we'd run into, so let's keep it. For our negative coterminal, you're going to start with your angle again. This time you have to subtract a rotation, so subtract 2 pi. But again, not common denominators. Let's change that to a 6 pi over 3. So 5 pi over 3 minus 6 pi over 3 would be a negative 1 pi over 3. You don't have to write the 1 down, of course. And then remember, I'm changing the directions for number 10. We're going to change the directions to say find all coterminal angles. So that's actually a really easy question. You just write down the angle. And then you're going to add a general statement of rotation. So plus 2 pi k. Plus and minus 2 pi k means the same thing. If you used an n instead of a k, it means the same thing. Those capitalized letters indicate any integer. So I don't know about you, but I'm kind of hoping my homework asks a bunch of those. Those seem easier. The general one. Oh boy, this might be the 4th class in a row where you've heard SOHCAHTOA. What is it? Ironically, kids still get these wrong. Go figure. Yes, I'm just going to modify that a little bit. I'm going to say sine of the angle, which I'm going to use theta, is opposite leg over hypotenuse. So it is a trig ratio, an equation, that will give you the relationship between an angle and 2 legs of a triangle using the sine function. So what does ka stand for? Let's change color. Cosine of the angle equals the adjacent leg over the hypotenuse. Very good. And then TOA stood for the tangent of the angle. Very good. Equals opposite leg over adjacent leg. And yes, you have to have these memorized. In addition to those, you also will have to have memorized the other 3. Who remembers the other 3? Just what they are, not what the formulas are. The reciprocals of them. Secant? Cotangent? Cosecant. You got it. Yep. Very good. And who they are, who they match with, we'll have to talk about in a minute. All right, so real quick, guys, just remember triangles are your friends. Number 1 mistake I find from kids is they're like, oh, these are so easy, because you did like 1,000 of them when you were younger. So then you try to take shortcuts, which is sometimes fine and sometimes not fine, especially if you don't show work. So set up the ratio at the very least. And I would like to see you guys approach these as equations, which is what they are. Sometimes your geometry teachers teach you really cutesy things like, if x is here, do this. Like, you're in PreCalc. You don't need to be told how to solve a proportion. You don't need a shortcut. You just solve the proportion. You got this, okay? Our angle measurement that they're referring to is going to be one of the remote angles, one of the non-right triangle, one of the non-90 degree angles. So this one that they're referring to is angle A. And even to this day, I will draw a little smiley face and pretend I'm standing right there, because it gives me a reference point for my triangle. So the 3.6 leg of the triangle, by definition on a right triangle, we call that the hypotenuse. How do I know that's the hypotenuse? It's opposite of, it's the longest leg, and it's also opposite of the 90 degree angle. That's the definition of hypotenuse. What would you call the 2 in reference to the angle that you're standing at? It is adjacent to you. So without doing extra work, if I want to use these clues, what trig ratio should I be setting up? Cosine, very good. So you set up the cosine of angle theta is adjacent over hypotenuse. Now this is where kids start trying to rely on shortcuts from their little kid life. PreCalc, you're better than this. I want you to solve for theta. Right now, theta is trapped inside of a cosine function. How do you undo functions in math? You have to apply their inverse functions. What is the inverse to a cosine? This is not a trick question. It's called inverse cosine. The cosine button. See what's right above it? Inverse cosine. So what you're technically doing, guys, is you're applying the inverse cosine to both sides of the equation, because that's how math works, right? So when you apply the inverse cosine to the cosine function, they cancel, and you get theta. And over here, this is something that you would have to type on your calculator. But wait, we have to remember something about our calculators. I want degree measure, so I need to go to mode, and I need to make sure that I'm in the right mode. So be in degree mode, and then I want everyone typing the inverse cosine to that ratio. And y'all should be getting the same answer. And methinks it's 56.3. Yes, and that is degrees. If for some reason you gave me a radian answer and labeled it as radian, I guess I would have to count you right because they didn't tell me otherwise, but that is a very strange answer for a right triangle problem. Just be wary that if your calculators reset, which they are almost on a daily basis for the yellow case, it goes back to radian every time it resets. So you're going to have to fiddle with your mode every time you guys work. Let's take a look at 14. So 14, this time the angle that they want me to utilize in my math, just use the one that they gave you, so angle B. So in reference to angle B, x is the hypotenuse, obviously. How do I know that's the hypotenuse, though? Because it's the longest leg, or it's across from the 90-degree angle, by definition, that's the hypotenuse. But what would you call the 25.6 when referencing angle 64 degrees? It's opposite of that angle. If for some reason you did a little subtraction problem and wanted to work with angle A instead, that changes your opposite and your adjacent leg. So it's not that you can't do it, it's just, why would you? Because it sounds like more work. So now I want which function if I'm using opposite and hypotenuse? Sine. Very good. So we're going to set up the sine of your angle. So this time we know the angle. Sine of 64 degrees equals your opposite leg over the hypotenuse. So 25.6 over x. And guys, this is a cross product. It's a proportion. Again, I know there's geo teachers out there who teach you if x is here, do this. If x is here, do that. And by the end of it, you have 17 rules that you have to remember. Guys, it's just a proportion. So when you cross multiply, you get x times the sine of 64 equals 25.6, and then you solve. So let's divide both sides by the sine of 64. And then even though it doesn't matter here, get in the habit of closing your sine function after the 64. It wouldn't matter in this particular case because there's nothing after it, but in the future there will be, possibly. And y'all should get the same answer, which is, yes. There's no unit of measure for the lengths of the legs on this triangle, so if you want to write units, go for it. I don't really care. All right, let's take a look at number 16. I got to get used to these new times. All right. 10:13. We get out at 10:13. Remind me of that. It feels weird, doesn't it? How'd you like starting later? It was refreshing.
5 minutes.
The hours seem longer? No, they're the same length. The passing period's longer. Yeah. All right, so let's go ahead and use the angle that they gave us. Let's use angle B here. That's me, standing at a B. And this 17 is the hypotenuse. And then x is next to me, but not the hypotenuse, so by definition, that's called the adjacent leg. So what trig function should I utilize if I'm having these clues? Cosine. So we have cosine of 60 equals the adjacent over the hypotenuse, and this is the one everyone loves because it's simply just a multiplication question. You're going to cross multiply cosine of 60, make sure you close the 60, the cosine function, times 17. And y'all should get 8.5, I believe. Cool. So that's a nice blast from the past. 4th year in a row. Yeah. Guess what kids screw up on the test? These. And you know why? Because they don't write anything down and then they just get really happy on their calculator and then it's wrong. And when your teacher can't figure out what you did wrong, even though it was probably something stupid and little, it's wrong. Oh, yeah. All right, so this is what Taylor was referring to earlier with the reciprocal functions. Sine and cosecant go together, and this is the abbreviation for cosecant. And when I was younger, it really bothered me that these are somehow going together because my dyslexia didn't allow for that to happen, I guess. So what I had to do was visualize like a gigantic like Superman S in the middle of this, and that's how I remembered sine and cosecant went together. There's actually a mathematical reason why they go together, which we'll discover later, but it just bothered me as a child. So cosine and secant are reciprocals of each other, and tangent and cotangent, it felt very obvious that they were reciprocal functions to each other. So again, things we have to have memorized as we move through pre-calculus eventually into calculus. So 19, it asked me to find the cotangent of theta. So first thing I have to get around is what is cotangent again. So from memory, I have to remember that cotangent is the reciprocal to tangent. And if I know tangent is opposite over adjacent, that means cotangent would be adjacent over opposite. So it's all a game of relationships. Like, I know tangent really well. Cotangent is just the reciprocal of that. So unfortunately, this is your angle theta. This is your point of reference right here, theta. I don't have the adjacent leg. So it's a very easy answer if you have your Pythagorean triples memorized. Do you guys remember that some triangles are called Pythagorean triples? Like, for instance, 3, 4, 5 is a Pythagorean triple. This is a 3, 4, 5 triangle that's been doubled. So I already know that leg is an 8. But if you guys were like, I don't know what you just said, that's okay. You're going to visit your old friend Pythagoras, and you're going to set up Pythagorean theorem. So the leg squared plus the missing leg, I don't know, squared equals 10 squared. And you're going to solve for that missing leg. So you're going to subtract 36 over, so 100 minus 36 is 64. And you're going to find out that that missing leg is an 8. So now I can go back and write, all they want from you is a value, which means they want a ratio for the cotangent. So adjacent over opposite would be adjacent is an 8. And then the opposite of you would be a 6. There's not a math teacher on the planet who'd be happy with that, though. This ratio reduces to 4 over 3. So the cotangent, whoop, is simply the ratio of 4 over 3. I'm not looking for a weird answer. I don't want you to find theta. I just want the ratio value. So let's take a look at number 20. Number 20 has a similar issue where here's theta. Here you are. I want cosecant, which is not my typical ratio, so I got to think about who cosecant is. It's the reciprocal of sine. Remember, a big Superman S in the middle. So the reciprocal to sine, instead of opposite over hypotenuse, it would be the hypotenuse over the opposite. Wah wah. We don't have the opposite. So I have to either know that this is a Pythagorean triple. This is, does anyone know what this one is? Really, the only kids who know are the ones who have studied them, or math team kids, because those are the only ones who ever use them. But they are really cool shortcuts in PreCalc and in calculus. This is a 7, 24, 25. So there's 3, 4, 5, 5, 12, 13, 7, 24, 25. There's a few that will keep showing up again and again, and maybe you'll end up memorizing them. But if you didn't know, you would just set up Pythagorean theorem. So make sure you're setting it up right, though. The leg squared plus the leg squared equals the hypotenuse squared. A little bit of subtraction here. 25 squared minus 24 squared, I believe is, or I'm not even going to guess. Is it? Well, I know what it is because it's 7. So 49. Okay. So x equals 7. But that's not the answer. That was just the leg I needed. So the ratio for cosecant is supposed to be hypotenuse over opposite. So here's the hypotenuse, and then you just found the opposite. So the ratio would be 25 over 7. How fun are those? So that's the thing about trig. And as you get into upper level mathematics, which, welcome, you're there. It's like a culmination of a whole bunch of stuff you're supposed to remember. And that's what makes it so fun. All right, let's take 21 and 22. I think we need to look at both of those. So 21, we have tangent of theta. Tangent's not a hard trig function for us. The problem is tangent is supposed to be opposite over adjacent, and y'all, we don't have adjacent. So we need to set up Pythagorean theorem here, and I don't have a shortcut for you. So your Pythagorean theorem is leg squared plus leg squared. So I always use x as my missing piece, so you can use whatever you want. X squared plus 18 squared equals, now for the hypotenuse, whether you're doing this on your calculator or mentally, you need to put 9 square root of 5 in parentheses, because you need to square both the coefficient and the square root of 5. Now, there will be a time in your life where you might have to do this without a calculator. It's not bad, guys. You just square the coefficient, and you think about what happens when you square the square root. So 9 squared is an 81, and then when you square the square root of 5, you just get 5. And this is 405. Okay. Now, those of you who are just typing away on your calculator, totally fine, except you got to make sure you use parentheses or careful typing. What's that, 324? 18 squared? Okay, I'll write that down. So subtract 324 from both sides, and you get an 81, I think, and then you get x equals 9. And again, that's great, but that's not even what they asked for. That was just us finding the side we needed. So if x equals 9, That's that missing leg. Tangent is, remember your theta angle is up here. Tangent is opposite over adjacent, so 18 over 9. There's not a math teacher on the planet who likes that answer. The answer is 2. Ooh, fun. Now, 22, I went crazy last hour, and I was like drawing triangles, which is usually the right way to do this question. And I was like oh, let's find the other leg, and then I stopped and actually read the question. What's the relationship between secant and cosecant? Oh, excuse me, cosine and secant? They're reciprocals. So what's the answer? Yeah, I really didn't need to do any work on that one. Sorry, first hour kids. I think we're going to hang everything up for this worksheet. Flip to worksheet 2. All right, where'd you go, worksheet 2? So, we're going to get as far into worksheet 2 as we can. If I run out of time here at the end, guys, your official assignment is worksheets 3 and 4. Hoffbauer was so kind to you guys. I think she circled the questions you're supposed to do, like on the entire packet. And she put bookwork, like photocopied on there. Yeah. We're getting homework done, people. It's going to happen. New year, new you, and all that. 2020, perfect vision. Let's come up with a little slogan. All right, so beginning of worksheet 2, you know, that's not really anything new. We just covered that already. This example, though, is kind of a testament to the kind of questions you're going to do for homework and eventually for your tests. They're going to be triangles where one of the legs is real icky, because this is the kind of stuff you end up seeing in calculus. So we just have to remember how to reduce radicals and then rationalize denominators when it's necessary. And obviously the trig component here is knowing all the ratios and how they go together. So number 1 is not done for you. And the first thing I notice is that they put angle theta over here in this remote corner. So that's kind of your point of reference if you want to think about you being over there. But do you notice how we don't have the hypotenuse yet? So there is no shortcut for this one. You just need to figure out Pythagorean theorem by setting up leg squared plus leg squared equals hypotenuse squared. So when you square root that and you reduce it, 125 square rooted would be like 25 times 5, right? So 5 squared of 5. I didn't go through and show the work of how we reduce the square to 125, but if you feel like, man, that's where I'm going to mess up, like that's a separate skill we can work on, okay? So this is just simply the length of the hypotenuse. That's not really what they wanted from me. What they want from me is all 6 trig functions. So what I'm going to do is I'm going to set up sine of theta, and I'm really guilty about this, so I understand, but try not to do this. If they want the sine ratio, you need to write sine theta or sine whatever the variable is. Don't just write sine, because that's like writing log with nothing in it. It doesn't make sense in math, okay? Now next to sine theta, I'm going to use his reciprocal buddy next to him. Who's the reciprocal buddy to sine? Cosecant, very good. I also need to come up with sine cosine, and the reciprocal buddy to cosine would be secant. And if you keep pairing them together, your brain will naturally put them together for the future, okay? And then our final guy would be tangent, and his reciprocal buddy would be cotangent. All right, 2 of these, they're going to be icky, and the rest are going to be fine. The first 2 that are icky are sine and cosine. So sine, remember, is opposite leg over hypotenuse. So like this is your opposite leg, right? This is your hypotenuse. So we're going to set up 10 over 5 squared of 5. But my math teacher's not going to be happy with that answer because the coefficients reduce. 10 over 5, that's a 2. So then I'm going to reduce that to 2 over the square root of 5. But my math teacher's not going to like that answer either. Why not? Because I'm not supposed to have I need to rationalize the denominator. So if you were to multiply top and bottom by the square root of 5, you'd end up with 2 square roots of 5 over 5. I didn't show the work there, but what you did is you multiplied by square root of 5 on the top and the bottom, and then you simplified, which there wasn't much to simplify. Now for cosecant, what I don't want to see you guys do is take this prettier version, not really pretty, and flip that one. That's a bad idea. Instead, why don't you take this version of sine and flip that one? So if I flipped this version, I'd end up with the square root of 5 over 2. That's a great answer. So it's technically up to you which ratio version is the one that you take the reciprocal of. So you want to look ahead and look at the one that's easiest to work with. So cosine, very similar. Cosine is adjacent over hypotenuse. So 5 over 5 square roots of 5. Math teacher's not going to like that one because the 5s would reduce to a 1. So that's 1 over the square root of 5. Math teacher's not going to like that one either because it's not rationalized. So we're going to hit top and bottom, numerator and denominator, by the square root of 5. And you get square root of 5 over 5. So once again, you can choose which version of the ratio you flip around. I'm going to choose that version right there. Because if I take the reciprocal of that version, I get just the square root of 5 over 1, which I'm just going to write the square root of 5. If, worst case scenario, you flipped the icky version, you just have to re-rationalize it, and the 5s would cancel out. So it's not the end of the world. It's just more work. And trig is all about shortcuts, right? We're always looking for shortcuts. Tangent. Finally. Nice stuff. Tangent opposite over adjacent would be 10 over 5, better known as 2. And the cotangent, I'm going to choose to flip the 2 around, and I'm going to write it as a 1 over 2. Yay, trig. All right, moving along. Well, lovely. Let's look at number 3. There's a little note down here from Mrs. Hoffbar. It says that you can technically use your Pythagorean identities to find all these answers. That is a shortcut for the future, I think. We haven't actually talked about Pythagorean identities yet in this class. It actually doesn't show up until the next trig packet. So once we get there, we'll show you what we're talking about. But just for those of you who are like thinking ahead for math team problems or maybe SAT problems, these identities, because they have relationships between all the functions, you can use them to solve for cosine, sine, tangent, all of them. All right, let's take a look at number 3. The way we're going to approach it today is we're going to draw a triangle. So you're all in for a treat. You're going to watch me try to draw a triangle. It has to be a right triangle, though. Nailed it. All right, so theta has to be one of the remote angles. I'm old and stuck in my ways. Theta is always this bottom remote angle for me. It could be anywhere, technically, at the top or the bottom. It just can't be at the right angle. And then the clue that they gave you is that the ratio for sine is 3 over 7. So that means the ratio for sine today that we're using is opposite over hypotenuse. So the opposite leg to theta would be a 3, and the hypotenuse leg would be a 7. Clearly, we're missing somebody. We don't have the other leg, and I couldn't even take a shortcut if I wanted to because there is no relationship between 3 something and 7. So we got it. Well, there is a relationship. It's called Pythagorean Theorem. Let's set that up. Ready? Leg squared plus leg squared equals hypotenuse squared. Let's see, that's a 9. So 49 minus 9 is 40. And then when you square root both sides, you would take the 4 and 10. That would be your breakdown, right? So it would be 2 square roots of 10. And already I'm not really excited about this because what this tells me is like the last question where we had a lot of weird rationalization. We're going to have that again. Bummer. All right, good news. I got lots of room. So sine, as well as his buddy cosecant. And then cosine, as well as his buddy secant. And then tangent, along with his buddy cotangent. All right, so again, 2 of them going to be a little funky. We'll deal with it. All right. I don't even have my triangle anymore. Here's theta. So the sine, oh, we already had that, 3 over 7. Which means his cosecant would just be the reciprocal of that, which is 7 over 3. Easy peasy, lemon squeezy. Let's talk about cosine. Cosine would be adjacent over hypotenuse. So adjacent to you would be this 2 square roots of 10 thing. So 2 square roots of 10 over 7. Which actually is a good answer, because it doesn't reduce and there's no radical in the bottom. But when I go to flip it, and I get 7 over 2 square roots of 10, this is where my teacher would not be happy with that answer. While it is reduced, 7 over 2 doesn't cancel out in any way, you wouldn't allow that as a final answer because it's not rationalized. So if you were to multiply top and bottom here by the square root of 10, what happens is you get 7 square roots of 10 over This is 2 times 10, right? Square root of 10 times square root of 10 is just simply a 10. So this is a 20 down here. That is your final answer for that ratio. So a little bit of tricky simplification. Like, this is not the first time in our pre-calc lives where the simplification could be the minutia that gets us. So you just got to go a little slow on that part. Tangent, let's see. Whoops. Opposite over adjacent would be 3 over 2 square roots of 10. Wah, wah. That's not okay. The only thing I don't like about that answer, the 3 over 2 is fine, but I don't like the square root of 10 in the denominator. So I'm going to rationalize it by hitting top and bottom by the square root of 10. And tangent ends up being 3 square roots of 10 over 20. Cotangent, I'm going to go back to this original version of tangent and just flip it around. So that's 2 square roots of 10 over 3. Whew, that's a good time. Well, we can't make it like baby trig. You're not in baby trig anymore, people. Big kid trig now. Let's take a look at, let's see, this is where I ended in first hour, and I don't want to like mess with their notes too much. Let's go ahead and do number 4 real quick. Secant. That's the clue they give you. Secant is 8 over 5. All right, secant of theta. So again, you can draw your triangle however you want. Just make sure that your angle theta is in one of the remote places. I like to place them in the bottom corner, but it's up to you. And then you have to remember what secant is. Secant is the reciprocal of cosine. So cosine is adjacent over hypotenuse, so this would be hypotenuse over adjacent. And again, that is something you need to have memorized, or at least the relationship between secant and cosine. So adjacent to you would be a 5 leg, and then the hypotenuse is a length of 8. And then wah-wah, I do not know the opposite leg, but I do know Pythagorean Theorem. So here we go. We got leg squared plus leg squared equals hypotenuse squared. Let's see. You think I'd be able to subtract? 64 minus 25 is 39? That sounds right. And then good news, that doesn't reduce at all. So we're just going to call it the square root of 39. Even though it's kind of ugly. Okay, sine, cosine, tangent, and their buddies. So I need sine and cosecant. I need cosine and secant. And tangent and cotangent. All right. Whew. Here's to hoping. So sine is opposite over hypotenuse. So we have the square root of 39 over 8, which I like that answer. Keep it. But your cosecant would be the reciprocal of that, which would start off as 8 over the square root of 39. But no one likes that answer. So don't overthink this, guys. If the original ratio doesn't reduce, nothing will reduce in the problem. So this just becomes 8 square roots of 39. Over 39. You can't read that. Okay, there we go. And then, cosine and secant, we kind of already knew secant. Remember, that was an 8 over 5. So that means cosine would be a 5 over 8. Tangent, though, we got to think about a little bit. Tangent is opposite over adjacent, so square root of 39 over 5. And then cotangent, if I were to flip that around, reciprocal that, not a good answer to leave it as 5 over square root of 39. Math teachers around the world want you to rationalize that, baby. So 5 square roots of 39 over 39. You guys are going to get so good at rationalizing. Yeah, fun fact, though. Turns out there's a wave in math where they don't really make you rationalize anymore. We just haven't hit all of it yet. So like when you guys go on to college, your professors are still the old school professors, my generation people. And we all rationalize, which means you all have to rationalize. So one day when you become a professor, maybe you can start a movement where no one has to rationalize anymore. That'd be great. There's really no point anymore. Anywho, I digress. So you guys are going to work on worksheet 3 and 4. The back side of worksheet 4 is bookwork, but it's copied on there for you. We still have to technically finish the lesson, but yes, it is very much review. So if you feel like working ahead, you go right ahead. New year, new you, 2020, perfect vision. I'm going to call your parents.